Okay. Good morning, everyone. I think where we left off was here, the last couple of slides of our previous presentation, Einstein's idea of stimulated emission, which leads immediately to the idea of the maser and then the laser. So it's interesting that his idea was done, came under the Bohr model, 1917, when the Bohr model was the best model that scientists had for the atom. And Einstein, in looking at the nature of photons, he came on the phenomenon which is called Bose-Einstein statistics. It's a terrible name, but what it means in layman's terms is that photons like to be like each other. They're very happy to have the same characteristics given the chance, as opposed to simple, we'll see with electrons, which are the exact opposite. Okay, with the Paulie exclusion principle, they cannot, in fact, have exactly the same states simultaneously. Photons like to be, and one of the aspects of this phenomenon is stimulated emission. And it's explained very nicely even under the Bohr model, which is where this came in 1917. So I thought this would be a natural place to mention this application. Stimulated emission is a simple idea, is that if you have the ability to raise an electron up to a certain energy level, let's say above its ground state, here's the ground state of V1. If you could raise it up to a higher energy level of V2, we know that if and when it would ever fall back down to E1, it would give off a photon of energy, this energy difference, whatever the difference is between E1 and E2, and that would come out as a certain wavelength, as a certain frequency, according to Planck's equation. H times nu here, we call it H times F, a frequency. What Einstein realized was that you could coax very easily an electron, which is in this higher energy state, to come down if you sent along a photon of just exactly that frequency, the frequency that this electron would give off if it fell back down to its ground state. This photon would stimulate this electron to fall down and therefore give off that particular frequency. It's the same frequency of the electron of the light which is doing the stimulating. Not only is it the same frequency, same color, same wavelength, but it also is coherent. That is, the light that's being given off will have the same direction as the stimulating photon, and most importantly, it'll have the same phase. That means the crests will line up with the crests, and the troughs will line up with the troughs, and the two photons will be identical, okay? The light all of a sudden will be twice as bright in every possible way. There's no interference here. There's no, destructive interference. So we call this coherent light. And this is the basic idea that which Einstein had. Come now to the great engineer Charles Townes, and he gave the first design, the engineering design. First of all, he did it with, it's called a maser. He did it with microwaves, something of lower energy, which could be more easily manipulated. And then the next round of engineers, after he showed the design, could do this with visible light of higher energy. And the basic idea is that you take a material, okay, in which you have an energy source, which you can pump up the electrons in that material. Here, I think the original material he used was a gas, like a neon gas. So some kind of a light source would, of just the right energy, would pump up many of the electrons in many of the neon atoms up to this higher energy level, okay? And this state of excited electrons would be just exactly the environment that you would want to start this cascading of simulated emissions. Well, we have a lot of these electrons now up at this higher state. Eventually, at one point, some of them are going to start to fall, and they're going to give off light. They're going to give off photon in all kinds of directions. But if you can engineer the design so that the photons going in one particular direction get reinforced, and the photons which are given off in other directions are not being reinforced, then this coherent light will build up, okay, as the photons, the stimulating of photons, go through the material. Particularly if you have two mirrors on either side, as this coherent light begins to go back and forth, continuing to stimulate other electrons which are up in that higher state, you have this energy source, right, which is continuing to pick up any electrons in the lower state up to the higher state. So you can have an outside source of energy which is continuing to keep what's called this population inversion, whereas instead of the electrons being in its normal ground state, being left alone, it's being pumped up, being agitated by this outside source. So as these stimulated photons grow and get brighter and brighter, that particular direction will build stronger and stronger, and more of the photons will be given off in this, direction along the axis of the tube. All you have to do then is just have one of the sides of the mirror be half mirrored, where some of the light can go out. So some of the light will continue to bounce back and forth to have this light being stronger and stronger, this coherent light, and some of it finally you can release. Okay? And this is the fundamental design, first of all, in the Townsend, of what's called the maser for microwave amplification by stimulated emission of radiation. And then the next generation with higher energies, the electrons could be brought up to a higher energy level where the drop would now not give you a microwave frequency, but actually a visible frequency. And that is the laser. Okay? And I don't have to tell you all the applications of a laser. Okay, just go to your checkout counter for the scanning bar, and also the wonderful stuff that can be done with eye surgery, for example. Okay, the last great hurrah of the Bohr atom. Bohr, as anyone working in the field of atoms, would have loved to explain the periodic table. Okay, of course, it's explained with Moseley with atomic numbers. And the reason why we stop at certain columns is because of chemical properties. But why do the columns are as long as they are? Why do we stop here at the noble gases? Why do they start again immediately after the noble gases? What is the actual structure that's going on here that's causing when you put them in atomic numbers with these kinds of rows, you get these kinds of families of common elements? This was still not explained. Well, the last great hurrah that Bohr had was, after Moseley, the holes in the periodic table were now well known, right? All the numbers that we don't have, the atomic numbers which we recognize, and we don't have an element associated with it, became the great hunt for many, many chemists. And the situation in 1913 was this element here, element number 72, was identified by Moseley, actually even predicted way back in Mendelev's day. And this was finally discovered in 1923 with the help of Bohr, looking at the spectrum of this element number 72, and therefore looking at the energy levels that are being given off, and looking at his model, as difficult as it was for multi-electron atoms. His model really only worked very well for hydrogen. Here we are up in 72 with 72 electrons. The complexity here, even the Sommerfeld's ellipses were not going to make this a simple and clear analysis. But Bohr did see enough that, according to the spectral analysis, given the energy levels of his radii, of his orbits, of his stable electrons, this thing should have the same kind of chemical characteristics as zirconium. You can see these kind of lines where the different elements would be in the same families. So he predicted that this element, when it would be discovered, would have similar chemical properties with element number 40, zirconium. And that was a very important clue for the chemists to go ahead and easier to know what you're looking for when you're looking for something, and they were able to discover and isolate this element, which they ultimately called hafnium, in honor of Bohr, because hafnium is the ancient name of the city of Copenhagen, where, of course, Bohr hometown, where his great institute was, where all the young students all over the world would flock to try to work with Bohr. So that's how the chemists gave it its name. And this really was, in 1923, the last great hurrah of the Bohr model. It was already on great shaky legs. Physicists knew that this model was not going to last. This was not the answer. It was not answering the fundamental questions that they were looking for. It only really worked for the hydrogen atom. Didn't quite understand why it even did that, because it was half classical physics and half this quantization. It wasn't a very coherent theory. But what was left anyway, and finally in 1925, when this element 75 was identified, there were 4 elements left in 1925, holes left with Moseley's analysis. And interesting story about these. Probably the most interesting being this guy here, number 43. So high up in the periodic table, but yet so difficult to find. Really kind of out there by himself. 61 also is pretty isolated. We're not surprised with these guys here that they were hard to find, because we know they're radioactive. We know all elements after lead are radioactive. There are no stable isotopes of any of these elements. So they're hard to find. They're disintegrating all the time with their half-life. They're producing their sister and daughter elements. Very difficult for chemists to isolate radioactive elements which have no even stable isotopes that will stay in one place for one time. They're all disintegrating in these complex chains. Well, it turns out that 43 was also radioactive. Surprising. An element so high up in the table have no stable isotopes. It's in fact the highest atomic number, which has no stable isotopes. All the other elements, certainly some of these elements do have radioactive isotopes, yes, but they all have stable isotopes. I mean, probably the most well-known that we would think of is carbon. We have carbon 12, which is very, very stable, and we have the carbon 14, which is radioactive, which allows us to do the carbon dating. 43 was an element as high up as it was that in fact has no stable isotopes. They're all radioactive, and that's what it made it so difficult to find these last 4 elements, ending with the natural element of uranium-92. I blocked out the elements beyond this because these were not even thought about in 1923, 1925, right? These are not found until we get, into much, much later time. So I just kind of blocked these out. So the story of these 4 elements and their discovery is very interesting, but would have to wait for a different time. But I did want to mention the discovery of hafnium with the help of Bohr's model. And the weaknesses of Bohr's model, the limitations, as we already said, it was very good to predict the hydrogen spectrum in terms of the wavelengths or the frequencies, but it didn't even do a good job in predicting the brightnesses, where the red line is brighter and the 2 violet lines are dimmer. His model couldn't even predict why this would be the case. And it was hopeless when we got to more complex atoms with more complex spectra to try to get his energy levels working and his photons falling from one energy level to another to produce these kinds of frequencies. Sommerfeld tried to help with his elliptical orbits to give more energies and more sophisticated kinds of energy levels based upon the shape of the orbits, based upon the orientation of the orbits in space, but to no avail. Okay, it just was too complex. Something fundamentally wrong here with this model. It had to change. Another big weakness was it could not explain bonding of atoms. Even something you would think it would be simple as the hydrogen bond, of hydrogen gas. Okay? Sure, chemists knew for a long, long time that these electrons were being shared, but what is it with the Bohr radii and the Bohr orbits that would make them share to go from, I don't know, one orbit from one to all of a sudden slide into the orbit of. Bohr had no way in his model and his theory to explain any kind of sharing of the electrons in any way. So most of the questions that chemists were interested in, the Bohr model could not explain. And so finally we get to really, I guess, the heart of our course with this presentation here, with the development of modern quantum theory. And it happens in a very short period of time, really, from 1924, really by 1928 or so. It's the theory, the fundamental theory of quantum mechanics is there. And in terms of the atom, has not changed fundamentally since then. A lot of work has been done in the nucleus and expanding it with a standard model with different fundamental particles way below the level of the atom. But the actual quantum mechanics theory of the atom, which is what we've been trying to get to in our course, really was done in the late 20s. And this presentation here that we're about to go through, I guess, is the centerpiece of our course. Is I'm going to try to explain as best I can the fundamental ideas of quantum mechanics. Before I do, I'm going to ask Greg, do we have any questions before I go on?
Peter, we don't have any questions. Tim Murray was asking if you're recording, because his sound is phasing in and out, and I'm having some difficulty too with your.
Oh boy, you know, I tried to fix this. I so apologize, guys. I tried to get a different modem which had a better output, not download, output to you guys, and I could not secure one, and that's why we're still limping along here. And I think this damp weather also doesn't help my signal. So I do apologize. I am recording absolutely, as they all are. They'll all be out on the YouTube channel. And I find when I play back the recordings, they're good because I guess I'm right here and I'm recording on my own machine. And so the recordings will not have sound problems. So please bear with me for the rest of the class. I hope enough gets through. If it doesn't, just go ahead and please feel free to log off and discuss and watch the recording when it gets out later on today, but I do apologize for this.
And then Peter, I have a question.
Yes.
The Bohr-Einstein debates, that whole thing, obviously Bohr won the debate, but I don't know what Einstein's model was that he was arguing against Bohr.
Yeah, no, he very good question, Greg. He didn't have an alternate model of the atom or quantum atom or anything like that. He was just criticizing what we're now about to go into is the modern ideas of quantum mechanics. He saw great weaknesses in the new theory that we're about to present, and he showed those kinds of objections. He gave certain thought experiments which show the weaknesses of the actual theory itself. He'd never proposed a different theory during that time of the debates during the 30s. We know as an older person, he began to work on his new theory, his combined theory of trying to get it right, but that was not during this time here. Here he was just being a gadfly trying to show the weaknesses of the existing theory to try to improve it in some way by people looking at these weaknesses. Okay, so here's our first slide I picked as a kind of representative idea. Here we have the Schrodinger equation, which I'm actually going to try to talk about. As crazy as that may be, I'm going to attempt to do this. Here's, of course, the famous Heisenberg uncertainty principle. Here the cloud chamber tracks for the antimatter, for the positron, which was predicted by the successor of the Schrodinger equation, the Dirac equation, which we'll mention here. And here is a Feynman diagram of the next generation of the quantum theory called quantum electrodynamics, which we will not have time to get into. But here's kind of a montage. Got this from the web of some of the fundamental icons of quantum mechanics. Okay, story goes that we have young Heisenberg, a graduate student of Max Born, We'll talk about these teachers in a moment. But Max Born basically goes to Heisenberg and says, you know, you're a really bright guy, and this Bohr model is a disaster. Um, you're the kind of person who could rethink this from the beginning and see if you can come up with something fundamentally different that can get us on a different track, because this track is dead. This is going nowhere. He literally challenges Heisenberg, the brilliant student that he felt he was, who of course he in fact was. One of his, maybe his most brilliant student of all the students that Born had, as we'll look at in a minute. And Heisenberg actually takes this challenge from his teacher and finds a way to develop, based upon very different principles, completely different, as we'll see in a second, than Bohr, to develop a new quantum mechanics, starting with your fundamental question, okay? What is the Rydberg formula? What is the spectrum of hydrogen? Can you predict that, you know, from the properties of the atom? Clearly, there are energy levels in the atom which are giving off these photons of these particular wavelengths, of these energies, and what is going on in the atom to make this so? Bohr had his wonderful model, which was successful for hydrogen, but not for anything else. And the story goes that Heisenberg was able to come back with an incredible paper that he gives back to his teacher. This is, I think, this is the beginning of something along the lines that we would like to see. And the paper begins with saying, in this paper, it will be attempted to secure foundations of a quantum theoretical mechanics which are exclusively based upon relations between quantities which are in principle observable. He's saying which clearly, you know, are not true in the Bohr model. And he goes on to make that very explicit. He says, it seems sensible to discard all hope of observing hitherto unobservable quantities, such as the position and the period of these electrons, these planetary electrons, and concede that the partial agreement of the quantum rules of the old theory with experiment, the partial agreement with experiment, is more or less accidental. This is this young, you know, PhD student saying to Bohr that your model, your correctness is really just accidental. And to try to develop a quantum theoretical mechanics analogous to the classical mechanics, in which only relationships between observable quantities appear in the theory. I'm going to get rid of the radii, the radiuses of your orbits, because we'll never see them. We'll never be able to measure them directly and detect them. I'm going to get rid of those kinds of quantities and only work with quantities which we can measure, like, for example, the frequency and the brightnesses of the spectral lights. And there are many other things we can measure. We can measure energy levels and things like that. But I want to build a theory that only uses measurable quantities, and because it's hopeless to work in a theory with quantities which are foundational, which we can't even measure. So this is the young Heisenberg with a brand new take on things. And here's just a little bit of his life. Here's the year 1925 when he produces this paper and comes back to Born with the paper. And as famously, he's using a mathematics. He's using a kind of constructing a mathematics almost from scratch that he has in his mind, which describes these energy levels, which describes these momentum levels, which he can measure. And he's using a homegrown kind of mathematics to develop these ideas to try to show what these energy levels would be and what their constraints would be and why the spectra would be what they would be. And Born takes a look at this thing and recognizes what he's actually doing is reconstructing matrices, which was something which was not really taught to physicists at the time. There was no application of matrices. Born, being a PhD in mathematics, educated by the greatest mathematicians of his teacher's generation, as I'll show you in a second, he knew this mathematics and recognized it for what it was, and enlisted the help of one of his other graduate students, Pasquale Jordan, Jordan right here. And together, the three of them take Heisenberg's physical ideas and his mathematical ideas, which would try to express it, and begin to really use the formalism of matrices to put it into a coherent framework. Heisenberg says at some point in his writings later on, yeah, it was almost like magic. I stood back, and these two other people who knew, the language and the formalism of matrices just transformed my ideas into a mathematical structure that I was not even aware of, that made sense to me once I saw it. And then they continued on to write 2 or 3 classic papers in what became called matrix mechanics, because it was based upon these matrices, showing fundamental things like, for example, in the very next year in 1925, another good friend of Heisenberg, Paulie, Wolfgang Paulie, another student of Born, another PhD student of Born, actually took the matrix mechanics, was able to reproduce the energy levels and the brightnesses, and the brightnesses of the visible hydrogen spectrum, the first great triumph of this new theory, this new mathematics. So one other thing I'd like to point out about his rise in the world of German science, here he gets his PhD in 1923, and in 1927 he's appointed a professor at the University of Leipzig in the very conservative structure of German, academia in general. Never mind of physics. This kind of rise is just unheard of. But his talent was recognized in this way. His teachers, as we'll see, PhD under Sommerfeld, habilitation under Born, and then next year under Bohr, going to Copenhagen. Yeah, these are the big three. These are the great teachers of quantum mechanics: Sommerfeld, Born, and Bohr. And you look at the biography of any of these scientists who were born around 1900, people who were in their 20s in 1920s, the people who by and large founded the new quantum mechanics, were taught by these three people: Sommerfeld, Born, and Bohr. On the nuclear side, on the nuclear physics side, of course, we have Rutherford. And these are the 4 great teachers of physics to this generation born in around 1900. So here is a little bit. In the previous presentation I just closed, if you look at the end of it, after the end, there's some information about Rutherford and some information about Sommerfeld and his students. You want to go back and take a look at that. Here's just a little bit about Born. These names may not mean a lot to many of you, but Felix Klein and David Hilbert and Hermann Minkowski, these were his teachers. These are all the greatest mathematicians of their generation, and these were Born's teachers in Göttingen, which is the Bible, which is the cathedral of mathematics of the world at this time and for many times before and after. This is the tradition that Born came out of, and then went ahead and studied with J.J. Thompson and Cavendish. This is where he turned to physics as his main study, and then came back to Germany to be a physics professor and moved up through the ranks and became one of the great teachers. So again, I've pointed this out before. If you want to be a great scientist, yeah, you must be, a genius in some sort and work very, very hard, but it really does help to be mentored by great scientists yourself. It doesn't mean you're going to be, but it certainly helps. Some people don't. Some people were not really mentored by great scientists directly. Probably Einstein is the best example. Einstein really was a lone wolf coming up. Most of his teachers didn't have much respect for him. And Einstein never had any students. Einstein was not much of a teacher. Never mentored people like that, not like these three. So Einstein's an exception in so many ways. But these other scientists, when you look at their histories, you look at the Nobel Prize winners and see who their teachers were, these names just keep coming up over and over again of who these people are. And one of the, I guess, one of the abilities of these great teachers is to recognize talent and to take the time to mentor these younger people because they see in them the great talent and potential that they have. That's also something that you need to be a great scientist to maybe to see. And just to look at some of his, his students, these names here that you will recognize, Nobel Prize winners like Maria Goper-Mayer won her Nobel Prize in nuclear physics. She is the second woman to win a Nobel Prize in physics after Marie Curie. Here we have Oppenheimer, we have Weizsäcker. Here we have, of course, Paulie and Heisenberg, who came to work with him as a postdoc. We'll see Walter Heitler at the end of this, one of the great chemists who takes quantum theory and applies it successfully to chemistry. Enrico Fermi, Edward Teller, the father of H-bomb. These names, if you go ahead and Google all these names, these are all students, of these people. And they all studied with Bohr and Sommerfeld as well. It's amazing the tour that these guys did. And here's just a little bit about Jordan. Interesting story that he becomes a Nazi and joins the Nazi party, actually for a while as one of the stormtroopers as a young man, gets caught up in this crazy frenzy. And finally does join with the war. He joins the Luftwaffe and serves as an officer, an intelligence officer, weather analyst. But he stuck to his physics, and particularly the physics, of course, of Einstein, and Einstein fell into complete disrepute. Being a Jew and in the Hitler regime, all this Jewish physics was to be rejected, and so anybody who still, was working in any of Einstein's fields, particularly something like general relativity, was, just outcast, because this was not German science. This was not real science. This kind of nonsense. Even quantum mechanics was suspect because Einstein had played such an early and pivotal role in the beginning of quantum mechanics and its involvement with its development, as what Greg was talking about, trying to show its weaknesses, trying to improve it, et cetera, et cetera. Anything which a Jew, like the most famous scientist in the world, being Jewish, was of course just hateful to the Hitler regime. And because Jordan continued to work in those fields, he never got very high up, luckily, in the ranks, although I'm sure he wanted to be at some point. Turns out after the war, you can't arrest everybody, right, in the country. And so many Germans were, of course, rehabilitated. Many mayors and governors of places, towns came back, to govern their towns and their districts, even though they were in the Nazi party. This is a well-known story, trying to put post-war Germany back together. And actually, Paulie was instrumental in trying to rehabilitate Jordan and getting him a teaching position. Finally, that happened in 1953, and continued to go on as a good teacher and did good work once the frenzy of Nazism was destroyed. So I want to explain the Heisenberg uncertainty principle. And the explanation that you will read in Popular Science is wrong. And that's becoming more and more well popularized, that the old explanation that the reason why you can't know both the velocity, or more technically the momentum, of an electron and its position where it is simultaneously, you can't know those two things simultaneously to arbitrary precision. In fact, if you measure the uncertainty of these two measurements, their product will be always bigger than a certain number. That's the uncertainty principle. And Heisenberg is to blame because at some point in his writings, he does give the idea, well, it's kind of like, you can think of it kind of like. And he goes on to say that if you want to know the position of something, well, you have to look at it, you have to shine a light on it, and therefore a photon will knock it to a certain degree. And how are you going to measure something when you're knocking it around? And this is very much the explanation you'll read in a lot of popular science books, and it is wrong. And I want to try to introduce you to the correct idea that this is fundamentally a wave property, that these electrons and all the atomic particles and subatomic particles which have wave properties, we'll come to this idea in a minute. Heisenberg then sees that this wave property of particles on an atomic and subatomic level will lead to this kind of uncertainty, this kind of fundamental inability to know to arbitrary precision these kinds of pairs of quantities. And the explanation that I want to choose, which is not with me, of course, one that I've read many times, is using single slit diffraction. We know about double slit diffraction. We know all about that from Feynman's wonderful lecture where he explains that in such great detail. Turns out if you send a wave through a single slit, a single opening, you will also get diffraction and interference. A little bit more complicated to explain, which I'm not going to go into the details, but basically the wave, if you have a single wavelength coming out of water or sound or light or any electromagnetic radiation, you will get interference pattern. You'll get a constructive interference of a bright, and then a destructive of a dark, and then a light and a dark. And it'll be a pattern like this, not the even pattern of interference of a double slit, where all these bars are evenly spaced and basically the same brightness. You'll get this kind of a pattern where you have a central bright, which is wider than any place else, and then a dimmer, and then a more narrow bright, and then something of this pattern. This is called a single slit diffraction pattern. And this is a property of waves. And this is a better explanation of what's going on when we see the wave properties of particles. And so here's a bit of a better analysis of it. We'll have W stand for the opening of the slit. We'll have Z be the distance from the center bright to that first dim place, okay, the first dim. We'll call that the letter Z. And the distance between the slit and the screen that you're shining this light on or seeing the wave phenomenon on, we'll call L. And finally, the wavelength of light that you're using, we'll use a coherent light. Coming from a laser would be the best, make it simplest. One wavelength is coming out here of lambda. And it turns out you can create a formula, right? You can do the geometric analysis and find that Z times W is always equal to L times lambda. What's interesting is that L and lambda are constant. The distance to the screen doesn't change, and the kind of light that you're using doesn't change, and therefore Z times W is equal to a constant. And therefore, as Z gets bigger and bigger, W must get smaller and smaller, and vice versa, because they're always multiplying up to the same number. Okay. And so here is the experimental result of this. Here we have W getting smaller and smaller and smaller, and you see the center bright getting wider and wider, and therefore the value of Z, the distance out to the first dim, is getting bigger and bigger. Okay, so as W gets smaller and smaller, Z gets bigger and bigger. Okay? Fundamental property of light, okay? Explained by the geometric analysis of what's going on with the waves, which we did not do. I just simply showed you the evidence that this analysis is correct. Okay? Now we come to, say, electrons. Let's send electrons through a single slit. Turns out, as we'll see in a moment, you will get a diffraction pattern. These electrons see a diffraction pattern which will have, brightnesses and dimnesses, where electrons will pile up, equivalent to brightnesses, where electrons strips will not be there, hardly at all, kind of like dimnesses. We'll get the interference pattern created by the diffraction. And you would consider the diffraction here. Instead of the beam going straight through, they will diffract, they will spread out. Okay. Turns out that this very much looks like what waves would do. And it turns out it is. Okay, and we'll show this in a minute. So bear with me, because I wanted to finish off the matrix side of things, the Heisenberg, Paulie side of things, and then focus on the wave mechanics of Schrodinger and really look at that more mathematically. So that's why it's a little bit jumbled here, in which we're looking at the properties of the wave properties of matter before we actually get to its establishment. Okay. So again, if you look at the analysis of these electrons going through, okay, we see that they spread out. And we know from the analysis of the waves that Z times W is a constant. Well, here's the equivalent of Z, okay, how far out they'll diffract, these particles will diffract out from the center. And W is the size of the opening. Well, now that we're talking about particles, this Z number, which the diagram is calling P sub x, stands for the momentum of the particle in the x direction. Here's the x. Okay. And remember, momentum is a vector. Momentum not only has a magnitude, it's the mass times the velocity, it's the mass times the speed, it has a number associated with it, how big the magnitude, how big the momentum is, it also has a direction, because velocity also has a direction. Yeah, one thing is to know how fast you're going. It's another thing to know you're coming at me or you're coming away from me. That's important. And that's part of the component, a component of velocity and therefore of momentum. And so what you're capturing here in the diffraction pattern, the spread of the diffraction pattern, you're not capturing the different speeds, I'll give you that, but you are capturing the different directions of the momentum. So the Z number, which this diagram is calling P sub x, is capturing the change in momentum, the uncertainty of the direction in which the electrons will take as it goes through the slit. And the width of the slit, the W, of course, is a measure of the uncertainty of the position of the electron, because we know it's got to get through the slit. Okay, so it's got to be someplace between here and here. So diagrams calling this delta x. So here is a measure of the uncertainty of where of the position at this place. It's got to be from here to here, and the direction it takes from here is in these various different directions. And this first dim, the width of the center bright, will take as a proxy for the uncertainty in the momentum. And so we have this product here. The uncertainty of the momentum times the uncertainty of the position is in fact not equal to a constant, but Heisenberg is able to show is at least as big as a certain specific constant, which he's able to calculate. Planck's constant over 4 pi. We, of course, cannot go into the derivation of this. That's way beyond the time and the, the kind of math that we want to be involved in. H over 2 pi, by the way, is called H bar. And so H over 4 pi is H bar over 2. And the reason why H bar is so important is you'll recognize this. This is the quantization that Bohr used for the orbital angular momentum. Okay? It appears again here fundamentally in Heisenberg's uncertainty principle. Clearly not a coincidence, but one that we can't do the derivations to show why. So I don't have this bar really is a slash through the top of the H, but I couldn't find that. So I had to put the slash through the middle. So that's my H bar. So this is the Heisenberg uncertainty principle, its statement for momentum and distance. And this is a property of waves. And since electrons behave like waves, they will have this property. Of course, we know in all measurements always are subject to uncertainty, always. Okay? You can never know any measurement up to its final. It always depends on how many decimal points your technology can derive. And it'll depend upon what technology you're using and what space of phenomenon you're studying in. No measurement is ever exact. It's impossible to be so when you look at the theory of measurement. So what is Heisenberg's principle saying? He's saying in principle, you cannot get below a certain type of uncertainty a certain type of precision. In principle, no matter what technology you use, the wave nature of the thing that you're measuring will prevent you from doing that. The better and better you know the position, the better you can squeeze and know exactly what that position is, the less wiggle room that you will give the position of the thing you're measuring, the momentum, how it's moving, just blows up. It goes to places which you just cannot predict. It's fundamental in the phenomenon of nature at this level. Truly, one of the most difficult things to understand about quantum mechanics is the Heisenberg uncertainty principle. That's why I'm asking you to watch the Brian Greene presentation. Okay? He did a really nice thing when the pandemic started. He said, "What can I do, to like, do for people? Everyone's stuck at home." And he developed this visual blog that he did, I think, every day or every other day, where he took an equation, different equations from physics and math and stuff, and just talked about them. And this is a really good one, where he talks about this equation here, the Heisenberg uncertainty principle. The middle part is very mathematical, which please skip if you want. It's not at all important to the ideas. But as I point out in the email, the first 12 minutes is a very nice discussion of the true meaning of the Heisenberg uncertainty principle. He mentions this business about being knocked around by the photons of light, which is not correct. He addresses that directly. And then the last piece, if you watch the last 5 minutes or so, the 10 minutes, he really wraps it up and looks at the philosophical ideas. He does a much better job. He's much more skilled at this than I am, and is one of the great popular authors of physics over the last generation. He's a professor at Columbia. His books and his YouTube videos are very, very famous. The Elegant Universe and things like that. You Google him on Amazon, you'll see all of his books are very, very well. And he does a very good job with this short talk that he just does informally, explaining the Heisenberg's uncertainty principle. Much better job than I've just done here. So I feel that I'm doing such injustice to such important things that I want to give you an alternative. Of course, you can Google the Heisenberg uncertainty principle and get a million hits. What I feel responsible as the teacher is to show you, let me show you something which is good. Let me show you something which I found, which I think is worthwhile. Not the only worthwhile, but I don't want you to, I want to give you some guidance as to find something which I think that you'll understand and is correct and is worthwhile. That's what I'm trying to do when I suggest these different videos to watch. Okay, just to finish off, where we need to go is to talk about the fourth quantum number. Remember, the first quantum number, so-called n, can be 1, 2, 3, 4. Those are the fundamental quantizations of Bohr. Basically, they're aligned with the size of the radiuses of his orbits, which Heisenberg says are unmeasurable, so let's forget about them. The second two come from Sommerfeld originally. They're the elliptical orbits, how flat the ellipses are, how much of a oval they are, how long compared to how wide, and then how you can stick them in different orientations, right? You can have them go one way and go north, south, and east, west. That was the second and third quantum number, which again morphs into something else when we get to Schrodinger's equation. Well, this is the last one. The idea of spin comes from an experiment which I don't have time to talk about. Two experimentalists showed, again, this quantization, something where classical physics would show there will be a smeared out of a spectrum of values. What they found experimentally was only two individual values, two isolated unit values, could not be explained. These two theorists, Uhlenbeck and Goldschmidt, come along and explain it by saying what's happening is the electron is actually spinning, like the Earth is spinning on its axis. Never mind going around in this orbit. Okay, it's actually spinning on its axis, and that would cause a magnetic field. It would act like a little magnet, and that's what you see in this experimental evidence, that it only has these two values, because the electron can spin basically clockwise and counterclockwise. This was their theoretical idea, and this led to the fourth quantum number, when Paulie finally gets his hands on this and agrees to it, first he didn't, but when he finally sees the benefit of this idea, he gives the fourth and final quantum number, the so-called spin quantum number. A favorite attribute of electrons when you talk about entanglement. 90% of the examples of entanglement will be two electrons being thrown out, with opposite spin. Let me stop here for a second and also say, we're not going to have any time to talk about the different interpretations of quantum mechanics and things like, entanglement and the many worlds interpretation. So this is really, really deep stuff. And I don't want you to be listening to me to explain that stuff. Okay? I want to find people that are much more knowledgeable than me and much more skilled at presenting this stuff with much more time. And that's why I really encourage you to watch the Sean Carroll video that I recommended in the current email. Okay, he goes through this. He first does some review. It's called The History of Quantum Mechanics, which is not really, but he does enough, I guess, to justify. But the last half, he really talks about the different interpretations of quantum mechanics, the so-called Copenhagen interpretation, which I'm going to present as one which makes sense to me, but I want you to see the much fuller version, and it's an enormous field that you could study forever. It's still controversial. There's still no consensus of philosophers and physicists of just what exactly the meaning of quantum mechanics are, and I'm really not the right person to take you through that. I can only give you the barest of introductions, okay? So there are things which I want to try to present and things which I'm purposely staying away from, but I want to give you an alternative to start to look at those ideas and issues if you are so interested. And so now that we have the four quantum numbers, we finally get to Paulie's exclusion principle. Paulie, the best friend of Heisenberg, went to school together under Sommerfeld and worked very closely together. One of his great triumphs is to take the matrix mechanics and produce the Bohr spectrum, the hydrogen spectrum, both the right wavelengths and the right brightnesses from Heisenberg's matrices. But his other great contribution, which he wins the Nobel Prize for, is the famous exclusion principle that says that unlike photons, which like to hang together, which like to have the same properties, electrons are the exact opposite. There are these four numbers which will specify the state of an electron, and no two electrons in the same configuration can have the same exact four numbers. This is something he comes up with empirically, and then is finally justified by not only the matrix mechanics, but also by the Schrodinger equation. Okay? The first number, n, is just 1, 2, 3, 4. It's essentially Bohr's orbits. Okay? The next two originally come from Sommerfeld, which really depend upon the size of n. We'll go through this in more detail in a bit. And then the last number is just a spin number, traditionally being a plus a half and minus a half. Okay? And this idea that electrons have to be separate in their state fundamentally will become very, very important as we look at the structure of the periodic table. When we finally come to understand what the periodic table really is, this is one of the fundamental principles which create that structure. And just a little bit about Paulie. Again, you see the Sommerfeld, the Born, the Copenhagen. It's all the same. Okay? And here's one of his great triumphs is to actually formulate the exclusion principle from the theory of electron spin. Okay, so we are about to start wave mechanics, and I'm going to be very ambitious here. Guys, I ask you for your indulgence. We're going to try to do some math on a qualitative way. There is really, remember we talked about the three levels of talking about science. I can tell you lots of things about science. I can also show you the experimental evidence of why those things are so, or at least why they're reasonable. And then I can try to explain or truly describe why they're so. And when you're talking on that level, you're talking about the language of science, the language of physics, which is mathematics. I always try to show you the experimental evidence. I never just try to stop at that these things are so. I endeavor to do that whenever I can. I have to pick and choose when I try to truly explain, to make some attempt at truly explaining this. The fact that the mathematics is so fundamental to the quantum mechanics theory, the fact that quantum mechanics theory has these inherent limitations that we would see in terms of what other theories are in physics, historically and even now, even, you know, the theories of general relativity. Quantum mechanics is unique in that, for example, it has different interpretations. What do you mean? What do you mean? It's a physical theory. It's about the real world. What do you mean it has different interpret? Clearly, there's something very strange about the theory itself and what it's saying about reality. If we're going to get at that in any way, I want to introduce you as best I can to why that's so. So that if you want to pursue this, and there's, again, a million hits out on the internet to pursue the mysteries of quantum mechanics and all the crazy titles that you'll see, I want to try to give you a simple and kind of grounded introduction to the idea. I feel that's my role, you know, in teaching the course here. Okay. So the whole thing starts with de Broglie's idea that even particles have wavelengths. And that's where this whole thing traditionally starts. But before I begin, we've kind of finished with the matrix mechanics side of things. And do we have any questions so far?
Yes, Peter, we have some questions. And there's a long conversation about the fact that you were breaking up pretty badly previously, and you were just back until right now. So I'm hoping you can hear me.
Yes, I can. I can hear you well.
Okay, great. So Andy Chapman asks, will you talk a little about the de Broglie wavelength for the slit?
It's right here in front of us.
Oh, okay.
This is the slide.
And then Mary Covington had a thought, is if your signal would be more stable if you turned off your personal video. Just had the slides up.
My personal video.
What, the picture of you?
You mean me here? My little picture? Okay, how would I do that? Let me see. I guess, stop video. All right. I think I did that.
Okay, we'll see how
All
that
right,
works.
I did. I'm just a frozen picture of me now. I know what it looked like, so that's okay. Good suggestion. If this helps, that would be wonderful. That's true. This is one less thing which is being sent up to you guys. This moving picture of me. Very good idea. I love it. Okay. So de Broglie has this idea as a graduate student that if you take a look at Einstein's equation for the momentum of a photon, photons have wavelengths. Okay, here's the wavelength. The momentum of a photon is Planck's constant over its wavelength. Why don't we go ahead and turn the equation around and say that just to solve the equation for the wavelength is Planck's constant over the momentum. Well, let's write a real momentum. Let's write a mass times a velocity, and maybe particles which have mass and momentum, maybe they have a wavelength itself as well. Basically, if light can act as particles, why can't particles act as light? Why can't particles act as a wave? That's his crazy idea, and he puts forth as his PhD thesis. And his professors really don't quite know what to make of it. His thesis advisor, Langevin, as we know, is a very, very good friend of Einstein. He was the lover of Madame Curie for a while. Langevin is there at the Sorbonne, and he is his thesis advisor. And Langevin wants to be as fair as possible, and he shows this to Einstein. because he is coming from Einstein's fundamental equation of momentum. And Einstein says, this is not such a crazy idea. This maybe has some merit if we could have some experimental evidence behind it. It's just an idea. And so Langevin goes ahead and supports this with his other, committee members, and with the strength of Einstein, they let it go. But they do ask de Broglie one very important question. He says, "Do you have any idea how you could substantiate this with experiment?" And de Broglie says, "Yeah, I think so. If I'm right here, let's take a page out of I'm trying to think of the other good friend of Einstein who first showed the diffraction of X-rays going through the crystals. He says if these electrons, for example, are going to have a very, very small wavelength, let's send the electrons through a crystal just the way the X-rays were sent through a crystal to produce a diffraction pattern. Because that's what, if I want to show wave behavior, I know what I have to show. I have to show diffraction and interference. So why don't we try to have an experimentalist send these electrons through a crystal where we know the crystal, openings are very, very small, and maybe we'll get a diffraction pattern. A very excellent idea. This would be a very reasonable idea. So to show, traditionally you always want to show why this wavelength kind of idea doesn't show up in everyday life. Here's the traditional kind of calculation. If you do a baseball going 100 miles an hour, you look at its mass and its velocity turning into SI units. The wavelength is going to be 10 to the minus 34th meters for a baseball, traveling big league pitcher throwing it. And that's 100 billion trillion times smaller than the size of a nucleus. It is, totally unmeasurable, never will be measurable. But if you look at an electron moving at a decent speed and do its calculation, you get a wavelength of 10 to the minus 11th meters, which is in the X-ray range, which is very much in the ballgame. Okay, so we're talking about very, very ridiculously tiny numbers for anything, momentum of any kind of macro size. This is only relevant when you have things in the atomic and subatomic level. So before we get to the experimental evidence, I want to show you the last physical model of the atom, which is really not all that well known. Didn't last very long. What de Broglie is trying to do is save Bohr's radiuses, literally the size of his orbits, because it's the size of the orbits which determine the energy levels, which determine how much electrons go up and down in energy levels, which ultimately produce the spectrum. So he's trying to preserve those energy levels, which are, in the Bohr model, the size of the orbits. And he has a really very good idea. He says, well, how does Bohr quantize the orbits? Remember, by the angular momentum. He uses this quantity h over 2 pi. That's why it's called h bar. Okay? That's why it has its own name to it. It's ubiquitous throughout all the equations of quantum mechanics. It comes up so often they just give it its own symbol, h bar. Bohr said that it comes in multiples. N could be 1, 2, 3, 4, multiples of h bar. Well, this is the angular momentum. Well, in classical physics, the angular momentum is the momentum, mv, times the size of the circle you're going around. Okay, not a reasonable formula. Try to capture the momentum of something going in a circle. It's the momentum times the size of the circle you're moving in. So Bohr says this quantity is quantized in this way. Okay, well, let's go ahead and just solve for the size of the orbit. That's 2 pi r, right? You solve this equation for 2 pi r, look what you get. You get n times h over mv. There's de Broglie's wavelength, h over mv. So his idea is not so crazy. This is where his idea comes from. So the orbits, so lambda is equal to h over mv, so 2 pi r is nothing more than multiples of the wavelength, his wavelength, that electron will be going around at that particular orbit. And that's where the sizes of the orbits come from. The size of the orbits, the radiuses of the orbits come from the circumference of the orbits, and the circumference of the orbits come from how many wavelengths, how many of my wavelengths will fit into that circumference. You can only get a whole number. It's very classical, it's very physical, it is very simple in that idea, okay? It's about as far away from the new quantum mechanics. It's very much in the flavor of Bohr's model. So we can say that the size of the orbit, 2 pi r, we recognize the circumference formula, is equal to a whole number of his wavelengths, okay? And that's how he proposes why the Bohr atom is quantized the way it is. It's quantized because these orbit sizes are quantized in this natural way, because the electrons that are going around in these orbits have wavelengths. And the wavelengths determine how big the orbits can be, how big the circumferences can be. Okay? Not a crazy idea, but it's very much couched in classical physics ideas, because these waves that are, structured in this way are a good example of what we call standing waves. If you pluck a string on a guitar or a violin, we know the ends of the string are fixed, and so the number of kinds of wavelengths, the lengths of the wavelengths that you can have in a plucked string are therefore quantized, because they all have to fit into not a whole number of wavelengths, turns out have to fit into a half number of wavelengths of the length of your string. But still, there's a constraint on the kinds of wavelengths that a violin string can vibrate at. This is the analogy to the idea that Broglie is talking about, that there's a constraint on how many wavelengths can be used and what sizes they can be used, and they will in turn determine the circumference of the orbits, which will in turn determine the radiuses of the orbits, will in turn determine the energy of the orbits in Bohr's model. And so what we have is the electrons are now simply not just going around in these simple Bohr orbits, but in some way there's a wave, I don't know, in some way associated with the electron. Is the electron now a wave and it's not a particle anymore? Is it, nobody knows, okay? But is there any merit to this at all, except for this kind of these simple algebra kind of things? Is there any merit to it at all? Well, here's an early one that, again, de Broglie showed in his thesis. It was well known in the Bohr model that Bohr could calculate the radius of the ground state of hydrogen. Let's hope he could. Okay, but all this Newtonian equations, let's hope he could calculate the size of the Mercury orbit, the orbit closest to the sun. And he was able to calculate, it's very famously called the Bohr Radius. It's 5 times 10 to the minus 11th meters. The actual value is not important to us. Well, from the radius, you can get the size of the orbit. I can get the circumference, 2 pi times that number. So it's a number. This is the size of the radius of the Bohr ground state orbit. Well, from, again, the Bohr model, you can get the speed, the velocity of the energy. You can get also the velocity in the ground state, and therefore you can get the momentum. And so you can calculate the de Broglie wavelength. And when you calculate the de Broglie wavelength of the ground state electron going with this momentum, son of a gun, if you don't get exactly 1 de Broglie wavelength. These numbers are virtually the same. So what he's saying is the reason why the hydrogen electron, the solar electron and hydrogen is going around the ground state, because it has a wavelength dependent upon its speed, dependent upon its energy. It has a wavelength calculated from its momentum, h over the momentum, and that wavelength exactly fits around the orbit. Wouldn't the world be very, very simple if this could be simply generalized to all the atoms, and and we look at the uranium atom with its 92 electrons, and we could calculate all these wonderful waves, and they all fit in so nice and neatly into, this is never going to happen. Never in a million years is this going to happen. But this is the germ of the idea that Schrodinger starts with to begin wave mechanics. Okay? And the de Broglie wavelength is ultimately something very real physically. Okay? As we'll see in the experimentalists do take up de Broglie's idea. It's taken up in two fundamentally different ways right away. In 1927, famous American team of Emission and Germer, they take a bunch of electrons and they smash it against a nickel target, a metal target, and it's going to bounce off electrons, particles. Well, if they have a wave type property, then they would create some kind of a diffraction pattern. They would create some kind of an interference pattern where in some angles you would get a very high number of electrons bouncing off. And if you change it to a different angle, you would get very, very few electrons bouncing off. And then if you go to a different angle, all of a sudden there will be a lot of electrons. You would get this pattern of kind of like dark light, or heavy electrons coming this way, almost no electrons coming this way, heavy electrons coming. By knowing the energy that the electrons that they're using, okay, therefore knowing the momentum of the electrons that they're using, they can go ahead and calculate this crazy de Broglie wavelength. And if they were shooting light waves into this physical thing, it would bounce off with a diffraction pattern. They could go ahead and calculate theoretically the diffraction pattern that true waves had given off. And instead, they set up a detector which will detect electrons in terms of an electric current, the amps being given off. And sure enough, as they swing around their measuring of the current that's being given off in different places, they're getting the highs and lows just where the light diffraction pattern would given off. These wavelengths somehow or other are real, that the electrons are creating a diffraction pattern and therefore an interference pattern of strong current, weak current, strong current, weak current, exactly in the form that if you threw waves at it, you'd get brightnesses, darknesses, and brightnesses and darknesses. And they won the Nobel Prize for this. And they shared it with this fellow here, George Thompson, the son of J.J. Thompson. What he did was he took electrons of a higher energy, calculating the de Broglie wavelength being in the X-ray range. And instead of bouncing his electrons off of a target, he sent them through a target, very much like Rutherford going through the gold medal. But he wanted to capture the electrons coming through the other side. These are not now alpha particles. These are tiny electrons all going through. And he was looking for a diffraction pattern. He knew what the diffraction pattern would look like if he sent through light with the de Broglie wavelength, the wavelength which would have the de Broglie wavelength. He knew what X-rays would look like, okay, the diffraction pattern. So he sent electrons through with the de Broglie wavelength of these X-rays, and this is what he got. He got the same diffraction pattern. Somehow or other, these electrons are spreading out in a diffraction pattern, yes, so they're acting like waves, but they're acting like waves of the de Broglie wavelength. There's something real about this calculation of de Broglie of h over the momentum, because he's using energy, electrons of known energy and therefore known momentum. That's how he's calculating what he should get. And then experimentally, he sees it and he can experimentally reproduce it by using the wavelength, the de Broglie wavelength of real X-rays. Okay. By the way, the physicist I was trying to think about, of course, was von Lau. Von Lau was the first one who sent X-rays through the crystal diffraction grating to produce these original diffraction patterns. Okay. What's ironic, and we'll stop here. What's ironic about J.J. Thompson's son being the one who shares the Nobel Prize for showing that electrons have a wave property is that his father was the one who discovered the electron as the first subatomic particle. And now his son comes along almost exactly 30 years later to say, well, Dad, these subatomic particles that you first showed, first time in science, that there are such things, they actually are also, I don't know, they're also like waves. So quite something. Okay. And just to stop here, this is the fundamental principle, of course, of one of two types of electron microscopes. This is the transition electron microscope, where we send electrons through a sample of known energy, therefore of known momentum, therefore of known de Broglie wavelength, and we can go ahead and focus those using that wavelength, setting up electrical and magnetic fields to treating them just like waves, letting them bend the way, bending electrons the way light would bend, given that de Broglie wavelength, and sure enough, you get focused, incredible pictures. I don't know if you can read this. This is down to the 50 nanometers mark. Remember, violet light is 400 nanometers. This is to a resolution of 50 nanometers. So this is the transmission electron microscope based upon the de Broglie wavelength. Okay, guys, so we will stop there, and you can see our next slide. As scary as it is, this is what we're going to try to do next time and try to understand quantum mechanics. Please take a look at Sean Carroll's video before next week. Okay, so I'll let you go if there are any questions before we go.
Peter, well, first of all, Peter, when you turned your video off, you came in through much better.
Oh, who made that suggestion for us?
I did.
Mary Covington.
Mary Covington, and she would like a Nobel Prize.
Mary, absolutely. You are a genius. Why didn't we all think of that? Which is the characteristic of a brilliant idea, right? A brilliant idea has the characteristic, why didn't I think of that? Wonderful, Mary. Thank you so much.
You're welcome.
A simple explanation, a simple fix. Anything else we have before we go?
Yes, one question from Andy Chapman. You spoke about direction or vector. Does this factor into the last physical model of the atom, and if so, what way?
No, you know, not really directly. Of course, the energy levels and the momentum levels are all computed one from the other, as we'll see here in the next set of slides. But no, what de Broglie was trying to get at was, how do I explain the sizes of the Bohr orbits? And the way he explains it is by saying the electrons have wavelengths, and an even number of wavelengths will have to fit into any one of these orbits. That was his fundamental idea. So he was more interested in the size of the energies, you know, coming to the momentums, coming to the wavelengths. He really didn't need to worry about the direction of the wavelengths of the electrons he was thinking about, because they were going in the Bohr circles. So they were kind of contained in that way, in a classical way.
And that's it, Peter.
Okay, very good. Wonderful, guys. So we'll finish up next week. We will try, as crazy as I am, hang with me. Let's see if we can take a look at this equation here and actually make some sense out of it, which is very rarely done in the popular presentations. I'm going to give it a try. Okay, guys. See you next time.
Thank you.